So for 39, it gives you that there are two crates. So crate 1 and crate 2, which is slightly bigger, weighing 4 kilograms and 6 kilograms, which are both on the surface of a frozen pond, which acts as a frictionless surface for us here, connected by a light rope. So that just means we can ignore the weight of this rope here. And then someone pulls the 6 kilogram crate, so the big one here, horizontally with an acceleration of 2.5 meters per second. All right, and then it wants us to find out what is the acceleration of the 4 kilogram crate. So for this one, it's pretty easy. If this one is accelerating 2.5 meters per second, and it's connected to this one, or if this one's connected to this one, which is accelerating, then this one also is accelerating at the same rate because they're connected. So you can't accelerate this one without this one because there's a rope and they're connected. So the answer to A is 2.5 meters per second squared. Then B asks us, draw a free body diagram for the 4 kilogram crate, and then use that diagram in Newton's second law to find the tension on the rope that connects the two crates. So you have your 4 kilogram crate right here, and there's a force this way, which is the force of tension, and that's really it. You also technically have your normal force pushing up from the surface of the pond, but that doesn't really impact the tension of the rope. So then to find the tension, its force equals mass times acceleration, so it's being accelerated. Well, the 4 kilograms multiplied by the 2.5 meters per second squared equals 10 newtons, because 4 times 2.5, that's 4 times 2 plus 4 times 0.5, which equals 8 plus 2, which is 10. So that equals the force of the tension, and that is part B. So then for part C, it wants us to draw a free body diagram for the 6 kilogram crate. So you have your other box here, you have your force of tension acting backwards on it because this is a compression, so it's pulling both of them inwards. And then you have the force of, well, just the force of the person pulling, as well as your normal force, which again doesn't really impact this problem too much. And then it wants us to figure out what is the direction of the net force on the crate. Which is larger, the force of T or the force of F? Since we know that the object is accelerating that way, we know that the force here must be greater than the force here, so force F is greater than force T. All right, and then for part D, it wants us to use part C, so this, and Newton's second law to calculate the magnitude of F. There's actually another way that you can do this, which is a little easier, and that's if you imagine this entire thing, so the two boxes connected by the crates, as one object, because they act the same as one object weighing 10 kilograms, being accelerated at the 2.5 meters per second squared. Because they're not moving independently at all, so you can just treat them as one giant 10 kilogram weight. And then so again, force equals mass times acceleration. So your force is going to equal your mass times your acceleration. 2.5 times 10 is 25 newtons. And that's that.